This is the constellation of Cassiopeia, the Lady of the Chair. We are looking from the nearby star Alpha Centauri. This pattern is about what we see from Earth, except for this star. It is the Sun, and we are 4.3 light years away. We're going to look at the system of planets that move around the Sun. The planets shine only faintly with reflected sunlight, so we must dim our image of the Sun to see them. Time has been speeded up so that 1 year passes in 20 seconds. We'll keep track of the years as Earth traces out its orbit. We can't see the moon because on this scale it's too close to the Earth to show up as a separate point. The average distance from Earth to Sun is about 150 million kilometers, or 8.3 light minutes, or 1 astronomical unit. This is the unit in which interplanetary distances are measured. Viewers on the Earth would see the Sun changing position in the sky from month to month and moving completely around in 1 year. But from here, we're looking down at the solar system from above the North Pole. The Earth-Sun line rotates in a counterclockwise direction. Venus, the next planet nearer the Sun, also moves in a nearly circular orbit. The distance from Earth to Venus is continually changing. When these two planets line up with the Sun like this, we have what's called inferior conjunction, and the closest approach of the two. In this position, we have superior conjunction and maximum separation. The line is now rotating counterclockwise, but as Earth and Venus get closer together, the line will change its direction of rotation briefly. This happens around inferior conjunction, and during this time, if we were looking from Earth, Venus would reverse its direction of motion in the sky. This is called retrograde motion. The closest planet to the Sun, Mercury, is also the swiftest. Its orbit looks like a circle off-center. Looking from Earth, we always see Mercury close to the Sun. The angle between the two is never greater than 28 degrees. Note that around inferior conjunction, the line to Mercury also shows retrograde motion. Now let's look at the first of the outer planets. Here is Mars. Its orbit is off-center and not quite circular. When Mars is in conjunction with the Sun, it is farthest from Earth. Now watch the line for retrograde motion. At opposition, Mars is nearest the Earth. Here are the 4 planets nearest the Sun and their orbits. We can see that the speed in orbit decreases as we go outward. The orbits are nearly in the same plane. Around 1600, Johannes Kepler discovered 3 general rules, or laws, which describe planetary motion. The first law, The orbits of planets are ellipses with the sun at one focus. Here are the principal axes for the orbits of Mars and Mercury. The other two orbits are actually slightly elliptical. Here are the principal axes for Venus and Earth. Kepler's second law describes the speeds of the planets in orbit, saying the area swept out by the radius in a given short time interval remains constant. This law requires that a planet move faster when it's closer to the sun. Here's how the law applies to Mercury. And of course it works for the other planets. The third law specifies a mathematical relationship between the period of a planet and its average distance from the sun. The distances from the sun are in astronomical units. The periods are in years. The third law says that the distance cubed equals the period squared. Let's check this law. Yes, for each of the first 4 planets, the numbers agree to 4 figures. We must speed up our time scale so that 1 year goes by in 1 second and move back to watch the giant planets. Here are Jupiter and Saturn. So far, all these planets can be seen with the naked eye from Earth. We must speed up our time scale again now to 10 years per second. Here are Uranus and Neptune. And here is Pluto. Pluto has the largest and most eccentric orbit, and the one with the largest tilt. The orbits of Pluto and Neptune never intersect. Let's see whether these more distant planets follow Kepler's third law. Here are the distances and the periods. The numbers agree, but no longer to 4 figures, particularly for Pluto. Even today, Kepler's laws are remarkably accurate. But we must use the discoveries of Isaac Newton to understand and predict the motions of planets correctly.